Hey Doug, how you doing?
Good, Evald. How are you doing?
Oh, my oh, here we go. My sound is on.
Outstanding. Ben is here.
Hey Ben.
Hey, Evan.
Engineering. Are you guys getting together like via Zoom, or do you live close enough? What are you guys doing?
Yeah,
Doing Zoom.
yep, doing Zoom to phone problems.
Great.
So this is going to be 4.7, right?
Yeah, kind of 4.7 and 4.8.
Okay.
Well, let's get the show on the road. So I'll give you guys a second to stare at that. I'm not sure where the other persons in this class are, but this amounts to the book version of what I gave the other day. So there's one thing on this that's sort of brand new. So notice it's in metric, which is of course fine. And there's a 600 Newton force acting on the end. And notice this is kind of cantilevered. This is sort of the equivalent of what you see at the Grand Canyon, where you want to stick something out, or what you were talking about at your house, Evald, where you might have a chunk of your deck sticking out over the top of something. So you want to be able to reach out here. And so, you might have a bunch of weight out at the end because that's a bunch of people. Again, it's very contrived and weird that there'd be weight pushing at some weird angle out there, without showing a bridge or something sitting on it. And then there's a force right here, straight down. That's kind of nice. Straight down, it's only vertical. And then another force over here. But then what's this here? I don't think we've seen that before. What's this right here? That's also super weird and contrived. What's that about? Well, it usually takes forces to cause moment, right? But again, they're just arbitrarily saying, hey, by the way, there's 1,500 Newton meters of rotation there, just magically. Like, we don't know where it came from. It's just there. So again, that's a little hard to kind of swallow because you're used to sort of, I get it if there's a force area on it, but it's like, why is that rotating? Like, nothing's touching it. Why is it rotating? I don't get it. It just is. That's the idea. So what we'll do at the last part of today is I'm going to give you a problem that has no loads. Like, you have to produce them yourself, just so that you can kind of see where these things really come from and understand maybe a little bit of a real problem about this. So let's see if we can figure out what's going on. Again, so we have sort of three forces and one moment that are just acting on this. And we'll get into this later, but notice it's supported at that location A, it's just sitting on something. It's not actually attached. In other words, does it make sense? It could bounce up and down there, if you will. There's nothing attaching. It's just holding it. It's just sitting on it, if you will. Whereas over here, there's a pin, if you will. So again, can you tell it would rotate at that point? So it's almost like they want it to be able to rotate or something. But notice because it's pinned, that won't allow it to move left and right. Like that pin would actually stop that from happening. Later in this class, we'll actually look at that and we'll figure out what's called the reactions. Like what's the reaction at that point B? What does it want to do as a result of all these other forces on it? And we'll talk about the fact that it's going to have to be able to push back or to stop the overall force. Because what we're getting here is ultimately, like we did yesterday, kind of an unbalanced force. The net result is this does want to go up or down, right or left, and it wants to spin. And so we just need to see what that is. And then we'll later on figure out how those two joints or those two supports at A and B might stop that from happening and thus produce equilibrium so that this actually doesn't move. So we talked last time how it was a little bit easier if you start, because really what you just need to do here is figure out the sum of the forces in X, the sum of the forces in Y. Notice there's no Z again. This is nice. And a lot of times this is true in real engineering problems. You don't actually have it a three-dimensional problem. Beams are often really just two-dimensional. So I can just do this. I don't need a matrix. I don't need determinants and so forth to determine things. I can just do it by what I see in basic trig. You're more than welcome to use determinants if you understand that language and just understand that there's, you got to create your own X, Y, Z axis and so forth. But it's easier just to do it based on what you see. And we saw the other day that it actually makes sort of the most sense to take care of the sum of the forces in X and Y first, since the vertical and horizontal versions of those forces are what cause the rotation. So I'm going to do the same thing this time. So let's figure out the sum of the forces in X for no good reason. Let's see over here. So this would have an X component. And you can be a little creative about this. Like you don't have to use 30 degrees if you don't want to. You could figure out that since that's at 90, this would be 60 degrees. So if I use 60, then that adjacent, and I'm going to do what I did the other day, because notice I have a number of forces here, and A and B are already chosen. So I'm going to call this point C. So I'm going to call that the force at C in the X direction. So it's like F sub C sub X. So if I use 60, then it'd be 650 times the cosine of 60. I think I'll just move this down and make notes. 650 newtons times the cosine of 60. Do you also understand that I could get that same exact answer if I was using the 30-degree angle? Since that horizontal force would be up here, that's opposite of 30. So I could also use 650 times the sine of 30, and I'd get the same exact answer. Maybe your 112 teacher didn't teach you this, but sine and cosine, the co is complementary sine. In other words, sine is the same as the complement of the sine. Sine of one angle, sine of 30 is the same as the complementary sine, since 60 and 30 are complementary angles, meaning they add up to 90. That's where those names came from. So draw pictures, like just make sure you draw the right triangles out and don't screw it up. Let's see, I got to get into degree mode. And as always, please interrupt. I'm just trying to, I could just write down the answers and I've already pre-done this, but I just want you to have time to think. 650 cosine of 60 is 325. Exactly. That's kind of cool. So there's a sum of the forces in X. So that's got an X component. Great. Let's see. While I'm here, while I'm staring at that, maybe I'll, is this a good idea? I don't know. Since I'm staring at that joint and it's fresh in my mind, maybe I should take care of X and Y at the same time. So since Y would be coming down in that direction, I'll call that the force at C in the Y direction. And because it's in the other triangle up there, that'd be the cosine of 30. So force at C in the Y direction would be 650 times the cosine of 30. It's one option based on the triangle that I drew. So I get 562.9. I have no idea where to round this right now, but I don't really care. I'm just trying to learn this stuff. And I probably shouldn't be lazy. I should probably at least write newtons in the answer, even though I didn't write it anywhere else. And of course, stop and stare at that. Don't just push buttons. Stop and stare and think, okay, the hypotenuse is 650. And so wouldn't these other two be smaller than 650? And if you really want to check your work, Pythagorean theorem, 325 and 562.9, and make sure you get 650. It's like, okay, good. I know I didn't screw it up. And also stare at the fact that in that larger, this red and green triangle I grew up there, the red vector is way shorter than the green vector. The green vector is almost as long as the 650. So I'd expect green to be close to 650, but less than it, and then red to be significantly smaller. You know, do I see that happening? Yes, I do. So make sense of this stuff. You're trying to learn how to think, not how to get problem number 102 correct. You're trying to learn how to think. Okay. Then I'm going to move over to A. Well, notice that's 300 going straight down. That's easy. So maybe I'll just write it down. The force at A in the y direction is given. It's 300 newtons. And there is no x. And then I'm going to move over here to this 500 and kind of do the same thing. Notice I'm being a little careful as to where I draw these things. I'm trying to draw them pointing at the same exact spot. So I need a new letter now. So I'm going to call this point D. So this would be the force at D in the y direction. And because that's 60, this angle up here would be 30. So I could say cosine, 500 times the cosine of 30 would work for that. So force of D in the y direction would be 500 times the cosine of 30. That's one option. 500 cosine of 30 gives me 433.0. So I've got that force figured out. And then to stay consistent with color, how to get rid of that. I don't want to bookmark it. There we go. So I want the red arrow also pointing at the point. So that'd be 500 times the cosine of 60 then, I guess, in that picture. So the force, and I guess I should label it force at D in the x direction. Your book calls this using the scalar method. In other words, just do the calculations yourself. And I'm about to make a mistake, and I've already made this mistake earlier, and I just wasn't paying attention and didn't notice it till just now, but you see if you can tell me what it is. Force at D in the x direction, that'd be 500 times the cosine of 60. At least that's one way to do it. Cosine of 60 was a half a minute ago, and it's still going to be a half, so it's going to be 250. But what do I have to be careful with here that I haven't really been being very careful with? What mistake, if you will, have I been making?
Positive and negative forces?
Yeah. When you're using scalars, you got to concentrate on that. So I kind of forgot about it till just now. And that's the other reason why you want to be careful with the arrows. So now I'm just going to quickly go back and fix that. Force of C in the x direction. Yeah, that's positive. Force of D in the x direction, however, that's actually negative. So I got to throw that in myself. These D forces, every one of them is going down. So every one of them should be negative. And I think I'll throw them in there in blue just to kind of highlight the fact that I wasn't thinking about that. So now I've broke all those forces into their horizontal and vertical components. And so now all I got to do is just add them up and see what's going on. So sum of the forces in the x direction then would be 325 minus 250, which I think is 75. 75 newtons. And I want to kind of highlight that. Good. Aaliyah's here. Glad you guys made it. So it's kind of cool to see when you look at the very kind of the start of this. 300 wasn't contributing, but force C was pushing right, force B was pushing left. You have to think of this as like a tug of war. They're pushing against each other who's going to win? Well, now that I kept track of the positives and negatives, I know that answer. Same thing for y, super easy. Some of the forces in y, just add them all up. 62.9. Of course, that's obvious. It's going to be down because every single one of them is pushing down. So I'm really just kind of adding all of these together. 562.9, 300, and 433. That's approximately 1259.9. So I want to keep track of that knowledge. So I know what's happening now. Does it also make sense that do you understand what you've accomplished? What you've really accomplished is you no longer have three arrows, three forces pointing at this beam. You just got one, and that's a lot easier to defeat. That's a lot easier for you as an engineer to stop. Notice it's not static. The sum of those forces is not zero. So, you could sort of go back and make the note to yourself, oh, I guess that's right since it's positive. And I guess that's down since it's negative. And so if it isn't for those supports, which right now we're ignoring, all we're going to do in later chapters is just not ignore them. If it wasn't for those supports, then that beam is flying right and down. And so we're going to have to ask the supports to push back against them. Does it make sense even before we get there that since A is just a smooth connection, there's nothing holding it there, that B is going to have to stop that horizontal push of 75 to the right? Does it make sense it might not be able to, like those bolts rip out of the ground? The bolt that's in there through it might shear in half. Does it make sense? We got to make sure that support can handle that so that the sum of the forces can actually be zero. So we'll just add forces for the type of connection there is and say, hey, this can actually resist vertical forces. And this one can resist horizontal and vertical forces. This one can only resist vertical forces because it's not actually pinned. So we'll actually add those arrows ourselves later, and then we'll make the sum of the forces be zero, which is your job as an engineer. As I said, in many respects, we're done with this class right now. All you got to do is get better at it. Cool. So now I got to get moment. And they told me that I'm interested in the moment around A. How is this thing rotating around point A? So fine. Well, then let's go get all the sum of those moments. So last, what are the sum of the moments? And don't just say sum of the moments, say around A, so that you're telling yourself and everybody else what's going on. Now, do you agree that we used to have 3 force vectors, but now we have 5? Do you agree with that statement? Makes our life simpler. What are those horizontal forces? Force of CX, force of DX. What are those doing with respect to moment? Daniel, you tell us.
Sorry, I spaced out. Could you re-say the question?
Yeah. What are those X forces, force of DX and force of CX? What are those doing for moment around A?
They should be doing absolutely nothing.
You are exactly right. Why is that?
So they're going towards the potential axis XI of rotation. So if you take the cross product, it just goes to 0.
Yeah, they're pointing right at it. So they have force, but they have no distance. Does that make sense? They're not a distance away. The force would have to be like up here to be a distance away from A, and that distance perpendicular would be right there. But they're pointing right at it. So they're producing nothing. And notice they were sort of careful to draw the arrow touching the top of the steel member, and they were careful to label A on the top of the steel member, because if they weren't careful about that, like the problem I did the other day, if A was actually in the center of the beam, then they actually would be a distance away, but A is up on top, and so they're pointing right at it. So there is no moment due to X. So 2 of my 5 forces then are effectively gone. And so all I really have then is all of these force in the Y directions. But do you notice that the 300 also, for the same reason, makes no contribution? because it's pointing right at A. So it isn't causing any moment at all. So really I only have the force of Cy, which can you see? And I'm very interested that you just see this as easy and logical. So please interrupt if you don't. Do you agree that the force of Cy is causing it to want to rotate in what we would call the counterclockwise or positive orientation? Whereas this dy over here is rotating it in the other direction. So they're fighting against each other. That's clockwise rotation, which we often call negative. Let's scoot that over since we're going to need that 3 in just a second, and I can't see it. So the question is this becoming easy to you? Are you able to look at that and go, this is not hard. I totally get this. This makes perfect sense to me. So again, just to kind of write it all out, and because it's kind of a cool thing to do, you're more than welcome just to start writing numbers and get the answer to this, but just because it's kind of cool. You tell me if you don't think this is a good idea. Sum of the moments around A equals the force of Cy. Now, what am I going to call the force of Cy? Well, we'll get to that in a little bit, but it's basically force of Cy times a distance of 3, since that's how far away it is horizontally from A. It's 3 meters. And we decided that was called positive, so I'm going to leave it positive. And then force of dy times its distance is 5 away. And then we've got that weird, mysterious, just magically plus 1500 in there, which also is positive. We're just told there's a magic 1500 from the hand of God or something. We have no idea why. There they are. My question to you is, what do I replace this force of Cy? If I look back up here and I see that force of Cy was negative 562.9, is that okay?
No, I think we want it to be positive because it should be giving us a positive moment. So I think we're just using the magnitude of the force.
Yeah, like, do you see how the downward arrow is the reason I said it caused?
Yeah.
So this is the thing that, and this is interesting because I've had different students want to approach this differently. We could just write all plus signs for everything. Force times the distance, force times it's all plus signs. And then when you go in there and you put in negative 562, it'll automatically sort of fix that. But then you also got to do it with distance, because does it make sense that distance right there, 3 is 3 to the left? So that's negative 3. So you'd end up with negative 562 times negative 3, and the signs would just take care of the whole thing. If you're a person that kind of likes formulas and you don't want to have to reason and think about things, you just want to let the formulas, like we sort of had to do with the moment around a point, that big determinant, if you like that because you know that you're going to screw up if you use your logic, totally get that. That makes all kinds of sense. If you're a person that doesn't like formulas because you just think, what if I get something wrong? Like I can't understand it. I want to just reason about it. Well, then yes, as Ben said, we're going to have to say, well, that's a positive. In other words, the fact that I said the arrow was down and I stuck the negative in there myself, if you will, I knew that it was sort of rotating in that direction. So you got to be a little careful if you're using logic, which is what I'm using right here. Force of D is also just a force. Force of D in the y direction is 433. That was a mistake. Again, I think it's really cool to write your workout like this, where you're actually, taking the time to write down what it is that goes in there and then replacing it. It's a little bit of a wasted step in the sense that, you could just write 562 in there. I don't care what you do on a test, but it just kind of helps you. Remember, you can't afford to make mistakes as an engineer. You just got to get this stuff right. Cool. So what do I get? 562.9 times 3 minus 433 times 5 plus 1500. And again, notice units. I'm being a little lazy, but remember, this is And I should check this kind of stuff, but this is newtons and this is meters. And so that's when I multiply it, I'm going to get Newton meters. What was 1500? Well, 1500 was labeled Newton meters. So it was already, so I'm adding Newton meters to Newton meters to Newton meters. So stare at that, because, you know, they could throw you a curveball, in which case, like, does it make sense? Because that moment they threw in there of Newton meters is telling us we're in Newton meters. Had that 3 down there been like kilometers or, you know, some other unit, I would have had to pay attention to that. So I will, as I often say, sometimes maybe not write the units in, but it doesn't mean I'm not paying attention to them. So all that plugged in, I got 1,023.7 Newton meters. So big picture, man, not good. This thing is a long ways from static. It's rotating like a propeller and moving to the right and moving down. Like, this is not good. This whole thing is just falling. So are we done? What did they ask us to do? Replace the loading system acting on the post by an equivalent resultant force and moment at point A. Have we done that? Are we done?
No, we need to calculate how much force is on each of the posts so that the total moment's 0, both going up from the posts supporting the beam. So that the moment 0 and the vertical components of the forces get canceled out.
Yeah, and you're clear in chapter 6 when you say that. Now, they're not asking us to do that in this case. But just in terms of answering this question, and I know you were talking too, Ben, but you forgot to take your mic off. I saw that. But notice it says an equivalent resultant force, like singular. We got 2 forces right now. And a moment. Now, haven't we found the moment? I sort of feel like maybe I am done with the moment. I'm stopping here just because you might look at a problem and say, hey, I'll just go figure everything out. But sometimes it's kind of hard to understand what they're asking, like in the book, you know, is this what they're asking? Again, I'm giving you all the answers in the back of the book. And by the way, with respect to your homework, I'm trying to assign a limited number of questions that are, you know, very preparatory for the test and also the main things that you need to know. Of course, that's my opinion. But if you get them wrong in the back and you cannot figure out why, you and I should be talking. Do not just turn your homework into me. Really, I'm not. What I'm doing when I grade it, just for your information, is I'm looking at your answers and comparing them to the right answers, and I'm taking a quick look at your work. But it's on you to make sure that you're getting that you get it. Like if you do the work, you know, as I vaguely quickly look at it, I see your work, and you have the right answer, then I think, oh, okay, this person feels good about this. That's my assumption. Is that really the case? And I don't know, but make sure you're taking it upon yourself to say, you know, this problem was really hard for me. I didn't understand why this method didn't work, and eventually tried another method and it did, but I don't really feel very good about that. Like, that all matters. You got to bug me more. You got to send me a text and say, hey, can we get on, talk about this? Do not turn your homework in wrong. Fix it until it's right. And I'm more than happy to help you do that. Really important. So from yesterday's knowledge, maybe I'm still staring at this thinking, well, it says an equivalent resultant force. Is that telling me they just want one? You know, like, I might look in the back. If I was doing this as a student right now, I'd say, well, I have all the hard stuff. I'd look in the back and see what the answer is. And if they had the you know, if these were the answers, then okay, good, I'm done. If there was only one force where they had combined 75 and 1259, using a right triangle, okay, well, fine, I can make one force out of it. In my opinion, and I'm not sure, it says a force, like it seems to be singular. So it seems like it's wanting to know the force and then what angle it's at, but I'm not really sure if I looked in the back what I would see. That's why I said I generally would look in the back on this, because I already know I did sort of the math right. I understand the logic. So let's go see if we can figure that out. This is not hard. Draw a picture. It's super easy. I'm taking that approach. 75, and try to draw it somewhat proportionate. Do you notice how radically different those are? 75 and 1300. Like one is tiny and one is huge. So if this is 75, and I won't even be able to draw this to scale, then 1259 is massive. Notice I drew it down because it's negative, not up. So this is 75. The other was, I'll call it 1260 just to kind of round off. Again, as long as your work on a test shows that, I don't care how you round it. You might get the answer a little wrong in the book, but so what? Great. All I have to do is Pythagorean theorem then to get this. I'm going to call it, as I did yesterday, force resultant. We're always looking for the result. So if I Pythagorean theorem 75, square root of 75, the magnitude, I might as well write my notes clearly, the magnitude of FR would be the square root of all those added together. I hope you think, yeah, it's easy. 75 squared plus 1260 squared. When I do that, I get 1262.2. I'm just going to say 1262. So maybe that's what's in the back. They just said a single force. They didn't say what angle it was at. Maybe that's all that's in the back. And again, I'm not kidding. I actually really don't know what's back there. But since I can, let's also, figure out what that angle is. I can see from that angle that the tangent of theta would be equal to opposite over hypotenuse. So what I chose to call the angle is the angle, well, in this case, down from the horizontal, or I guess that would be clockwise from the horizontal. So when I do that, second tangent, 1260 divided by 75, I get a big angle, 86.6 degrees. Again, without the picture, that's not a good answer. Do you understand that? If you have the picture, you're fine, you're done. But you could also say, well, you could call it negative 86, and that would tell you that would tell the person it's actually going in the clockwise direction, which is negative. Or you could write clockwise, whatever you want. But finish it. So there, I got one force. If what they meant was a force, now I got it. Now, I think you would agree that the other part of this is confusing. By an equivalent resultant force, all three forces are now one. I just did that. And couple moment at point A. That's a little bit of a confusing language. I thought couple moment was like two parallel forces pushing against each other that were exactly the same size. I mean, that's kind of like, what? Well, let's just play around and I'll show you what that means. So would you agree that because some of our moments was positive, then positive means counterclockwise rotation. So it's wanting to rotate counterclockwise. What does that tell you about where this force is located? And when I say this force, I mean this single force right here. Where is that located on the beam? Where did Leah go?
At point A.
No, it's not at point A because it wouldn't be, well, actually, I got to think about that. Yeah, remember, there's nothing on the beam now except for that arrow. It's all gone. There's nothing there except for that arrow. And if it's causing counterclockwise rotation, then where is it? Notice it's pointing down.
That's C.
Yeah, now it's not at C, but it's between A and C somewhere at least. By the way, does it even have to be on the beam? The answer is no. It could be actually be clear off the beam. Remember, these forces, you're replacing it in terms of how it's behaving. It's not actually there. So it could actually be even clear off the beam for all we know. Well, let's try to locate it. Unfortunately, I don't have really any good spot to do it, so I think I'm going to draw it from scratch, just so I don't make a mess of the drawing. So there's our single force. What about its location? So let's see, do I care that that's there? Yeah, I guess I do. I'll put it on top where it's supposed to be. So there's point A. So my force is actually kind of over here somewhere. My force resultant is over there somewhere. And so that's agreeing. That's causing clockwise rotation. You good with that? So I know it's over there. The question is, what's its distance away? Does it make sense to you that the force of R only in the y direction times d would have to be equal to the sum of the moments around A? Do you agree with that? So we figured out the sum of the moments around A was 1,023.7 positive. And the force in R in the y direction only is 1260. Again, I'm using logic. I'm not thinking about that being negative. If I was, 1260 would be negative, but then does it make sense D would also be negative? So it'd be a negative times a negative is a positive. So that's easy. All I gotta do is solve for D. If I take 1,023.7 and divide by 1260, I get 0.8. I'll call it 0.81 meters.
So why are we using only the y force and not the full?
Yeah. Why do I not want to use the entire 1262?
Wait, I think maybe I see it because it has to be the perpendicular force, right?
Exactly.
And
Got to be perpendicular. So can you use 1262? Yes, if you want to try to calculate the perpendicular distance to it, but that doesn't look very easy. So it's generally easier to change the force than it is to change the distance. It makes the geometry a lot easier, if you will. What do you think? Filled with happiness? Again, if I look this up, I'm actually really not sure. I'm not sure if I've answered this correctly because I don't totally understand what they're asking. Like, where's the couple moment? Where's the other force? I mean, what are you talking about? Just for the fun of it, let's go stare at something. And by the way, this is one of your options. Anytime you want to get with me on a quick Zoom, here's something I have available to me that we can steal. So I'm going to go into engineering 211, go into solutions, into chapter 4. So I have the PDF solutions from the author, and they're not always, they're correct, but they're oftentimes not very easy to read. But I'm just curious, like, what does he think the answer to this question is? Unless I made a math mistake, I know I did all the math right. Let's see what he thinks the answer is and see how he did it. Did he do it like we did it? I like this. Notice that he said 75 and he drew a little arrow on there just to tell you, hey, it's right. Like, that's a little better than just positive, isn't it? And he drew a little arrow that says down. I kind of like that. And that's our answer, right? Except for, let's see, was that our answer? Yeah, minus rounding and so forth. So what's with this answer? Is that okay? My answer was 1,262 newtons. Do you understand why his answer was what it is? You can't have 4 numbered answers. So he said, oh, kilonewtons, scooted the decimal over. Based on what I did, I would have said 1.26 kilonewtons because mine was 1262. Apparently, I sort of rounded a little bit too much too soon. Do you agree? You see what I'm saying? Again, as far as your homework goes, or even a test, don't redo it. But that illustrates if he's right, if he hasn't made a math mistake, because he carried this 1295 out further than I did. That illustrates kind of why rounding is important to save for later. Did he get the same angle we got? Yeah, pretty close. I got 86.6. Notice he has a little picture there to describe what direction he's going instead of saying positive, negative, counterclockwise. I don't care. Just make sure you communicate it. What's not going to be good is if you say 86.7 without a picture, because that implies positive. So you got to at least do something. You got to say negative in this case or draw a picture. So I had a right triangle sitting there. So essentially that's what I did. What's this? I'm reading this right now because I don't understand. Oh, he never made a calculation for the rotation yet. I didn't notice that. So we got 1,023.7, 1,023.69, and then he just called it kilonewtons, 1.02 kilonewtons. Okay, so we didn't get that wrong. Again, notice he said counterclockwise. That's true. Isn't that what we got? Counterclockwise rotation. So then
Unknown caller.
Then he drew a similar. So notice, yeah, that's the answers we got. So my interpretation was right. He really did want, the author wanted one force. So it's force in a direction. And then that resultant rotation, that was the answer. Like notice there was nothing in here about locating the point. It didn't say where, he didn't say it had to locate it. So I didn't read the directions carefully. You didn't actually need to locate where that was. Again, this isn't, I'll show you one other thing really quick. Because we didn't talk about this very long, and it's also because I don't think it's inordinately important. Notice the word couple moment kind of didn't even really figure into the answer. You just kind of listed the moment, right?
I would have thought when they said that, then they meant that you should put another arrow in the same place going the other way, and so it would counteract it or something.
And remember that that's kind of what this means, just in hindsight. If I draw an arrow aiming right here, perfectly parallel to the other one of exactly the same size, notice that doesn't cause any rotation. But the couple moment thing was you just take F of R times D and that gives you the answer. Even though there's two forces that are exactly the same opposite of each other. So there's the other location. But as I said the other day, realistically, what that means is that's what you're going to have to do as an engineer to stop all this from happening, if you will, is put a force that's right there. That'll stop the vertical horizontal rotation. I'm sorry, the translation. Anyway, good enough for now. Okay. So here's something I do all the time that I'd like you to stare at a little bit. So I'm doing this constantly. So what I want to do now is give you a problem like we just did, but I just want to kind of take you through it. I mean, this is actually kind of my first project. If there was a way for me to, I don't know, we'll see. Maybe I will give it to you as a project, but this is an actual drawing from the engineer that I use to help me draw house plans. And in this particular case, Notice down here it says basement slab. And so the gist of it is this. There's going to be living space down here and people that live and work down there. So notice it's an 8-foot tall ceiling. And so that's kind of normal for a house, an 8-foot tall ceiling. So you got a place to live. But notice it's called a retaining wall. Retaining. What is it retaining? Well, there's something out here. And in this case, that something is dirt because the house is built on a hill like this. So how do you build on a hill like that? Well, what you usually do is you come in and oftentimes you come in and you chop out a flat section right there out of it. But of course, when you chop a flat wall against the dirt, that wants to tip over. So then you come back and you put a foundation wall in it like this, so that now this dirt has something to push up against. And then you kind of build your house on top of that. And so on this side up here, it looks like a 1-story house. But then down below, it's effectively a 2-story house. So from the back side, 2 stories, front side, 1 story. When you build in a hill, you kind of don't have a choice but to do that. The only other option would be like pile rocks up in the downhill side until it's flat, and then you could just build a flat house up there, but that's just super expensive. So this kind of happens all the time. So can you appreciate that this dirt over here is putting force on this wall? So that's where the force comes from. Like that's where all these arrows come from. But this is worse than what you're doing now, because how many arrows are on that wall? Last problem we had, there were 3. How many arrows are on this wall? Well, the answer is like 3 million. And it turns out they get bigger and bigger and bigger linearly as they go deeper. Do you understand why that would be? Think of it as water, and that maybe helps a little bit. But the deeper you go, the more water there is, and so it's heavier. So those forces just get bigger and bigger and bigger. So what we'll talk about, this is that we weren't going to focus on that right now, just because you don't understand it yet, because we got to somehow, how are we going to do that? If there's a million forces, how are we going to sum up a million forces? And so again, the cool thing is later on, when we do what's called the distributed load in this class, which is commonly the way it's done, there's never just 2 forces on a beam like we're studying right now. We're going to talk about how to reduce that to just 1 force and know exactly where that force is. Now, I want you to look at this carefully. So for now, as I said, we'll get back to this later. Turns out that single force is about right here. So let's say that was really big. You tell me what's going to happen to that gray foundation. Now notice it's got rebar in it to hold it all together and stuff. But if you went up and you pushed on that, just like you got a calculator sitting on your desk and you push on it, I want you to tell me what's going to happen down here if this thing is sitting on the ground right here. What's going to happen if I push on that? Assuming it's all connected together so that it doesn't break.
It's gonna go up. I mean, the left side is gonna go up.
That's exactly right. What point is it going to pivot around when it goes up?
Center of mass.
Not, it would if it was in the air.
Oh, but here,
It's on the ground.
the bottom, just like the middle bottom point, maybe around where all 3 of those beams kind of intersect.
What about maybe the corner of the foundation, like the far bottom corner?
That's where it's going to go right there.
Yeah.
Oh, that's right. Yeah.
So engineers call that the toe. Can you picture? And it kind of looks like a foot, doesn't it? Like if you lean forward, if somebody pushes you forward, doesn't all your weight, doesn't your heel come up off the ground? As either Ben or Daniel said, your heel is going to come up off the ground. So the back of that's kind of the heel. So it's going to kind of do this, isn't it? Isn't that what's going to happen? Again, assuming the whole thing stays together. Does it make sense if you don't have all that rebar that what would happen would be this? Do you notice where that rebar in the wall is right there? Is it in the middle of the wall? See that rebar right there? Is it in the middle of the wall? No, it's in the back of the wall. Do you see why? Because in this drawing down here, this heel is what's going to separate. And so if you have the rebar in the back, that's going to keep that from lifting up off the ground. Does that make sense? That's real important. You don't just put rebar in the wall. If the rebar was actually incorrectly placed in the front of the wall, does it make sense it would just tip right over because the rebar isn't stopping that from happening? So that's your job as an engineer to understand that. When you go out on the job site, the concrete guys, they don't understand that. So they're just going to put rebar on the wall and you inspect it and tell them, dude, you can't put that rebar there. And then they're going to cuss at you. And you got to know your stuff enough to help them explain, you know, like why that's got to be done a certain way. See, even has a note on it. It's so important. Number 5 dowels. 5 is 5/8 of an inch diameter on soil side, like bold letters underlined on the soil side of the wall. Do you see why that is? Extremely important. So does it make sense? All you have to do to figure this out is to figure out what's called the tipping moment is, and again, that's what engineers call it. The tipping moment is if this was say 1,000 pounds, does it make sense you just be multiplying by that distance right there? That's the perpendicular distance. So if you knew where this blue arrow was located, that blue vector, if you knew where that was located, then you could multiply it times the distance d that you would know, and you would know how badly the dirt wants to tip that wall over. Does that make sense? So my question to you is, what's going to stop that from happening? And that's what I'd like to show you now. Do you have any questions about what you see there, just out of interest? Notice there's a bunch of dimensions down here that are given. Notice right there, it's even called the toe and called the heel. Overall, this thing is 4 feet 4 inches.
Is there on the heel, the force is gonna go straight down from the ground, pushing on it?
Yeah.
Right.
So one of the forces stopping that is all of this dirt right here is piled up, pushing down right there. Does it make sense? That's resisting it. That's part of the resisting moment. So I usually pay somebody about $1,000 to calculate this. And what I get back from them is all of these notes and the dimensions of all of this, and the important dimensions that you probably understand now are these down here. Like, how big does the footing need to be? So let me show you so this is the same exact drawing, but I drew this myself in AutoCAD. So this heel distance down here a second ago, he said was 1'4". I just called it 16 inches. The wall itself was 8 inches thick. And then the distance from where that wall hits out there, he called it 2 feet 4. I just called it 28 inches to make it a little bit easier. I'll show you why in just a minute. So take a look at this. This is kind of cool. So this is pretty neat. So the whole thing wants to tip over based on this toe right here, thanks to that single blue force of the dirt that we'll talk about later in this class, which is approximately right there. Force of dirt, I guess I'll say. Or maybe force of soil, since they called it soil. That's what's causing it to tip over, creating the tipping moment. Well, do you see now that I put a house on top of this, what's going to keep that from happening? So let's see if we can figure this out. Floor load. Let's just look at one example. Floor load, 12 feet of tributary. And by the way, what you're seeing here is a 1 foot slice. If we can sort of get this 1 foot slice not to tip, then every foot down the wall will behave exactly the same. So that floor has 12 feet of tributary. Notice it has 40 pounds per square foot of live load and 10 pounds per square foot of dead load. Again, live load is people, hot water, or beds, water beds. Somebody could bring hot tub in there, whatever, like anything that moves, furniture, stuff like that. And that's the calculated value. That's the real value for residential load is 40 pounds live load. But does it make sense you can't count on live load? Because when you first move into the house, none of that stuff is there, right? So up here at the top of this, I said dead load only. So you have an understanding of tributary. Let me show you this. If this was the floor and it was 24 feet long, does it make sense that all of this side of the beam kind of bears down over here? And all of the other side of the beam bears down over there? So that's what must be going on, because this is 12 feet of tributary. That means the house must be 24 feet wide, and the 12 feet on this side is actually what's there. So if you take 12 feet times 10 pounds per square foot, that's 120 pounds. So basically you have 120 pounds right there pushing down. Now that's not very much, right? 120 pounds. So since this is toe, I'll call it T. So what I want you to try to figure out is the sum of the moments around T. And I'm going to do the first one for you. Now, this 120, where is it? That's a little debatable, but I'm just going to put it right on the outside edge right there. That's 120 pounds. It could be argued it's in the middle of that wall. Could be argued it's on the inside edge, but I'm just going to put it on the outside to keep it simple. So, moment around T. The house is going to be causing counterclockwise rotation. So my question to you is, it's 120 pounds times what for a distance in this drawing? How far is that from T?
I'd say 36 inches.
Yeah, 28 and 8 is 36 inches. That's exactly 3 feet. So because I want my units in foot pounds, remember those are the standard way this stuff is measured is foot pounds. I want all of my, I guess I'll write that in there just so you have something to reference, but 120 pounds times 3 feet. There's my first resistance. Can you see that resisting the blue force? Can you see that it's because it's on the other side of the toe? And this is what ends up so important in engineering is how long does that toe need to be? Does it make sense if that toe is a lot shorter, then that 120 might only be multiplied by 1 and now it's not near as effective? So an engineer is actually coming up primarily with that number right there. How big does that toe need to be to keep this thing from tipping over based on the weight of the house? So what we're calculating here is, as I said on the top, what's called resisting moment. There's tipping moment in the language of real engineering, and there's resisting moment. So we got to resist it. Whatever that tipping moment is, we got to have more to resist it. Otherwise, this thing falls over. So notice, no arrows on this. There's no arrows anywhere. You got to put them there yourself.
Unknown caller.
And notice I've got the abbreviations up here so that you know what they stand for. So I'm looking at this wall load next. 8 PSF, pounds per square foot, all dead load. Why would a wall be all dead load? Where's the live load?
Because you're not going to be frequently applying weight to the roof. Although technically, if it snows, then you have to accommodate for that.
Yeah. Now the roof is a separate number. We'll look at that in a second, but you're right. You can't really do much to the wall. You can hang a picture on it, but that's kind of like a fly landing on it. You can't really do much. There's not really a live load. You don't take things on and put things off of walls. So it's 8 pounds per square foot. Remember, this thing is only a foot deep. It's only kind of a foot into the page. And notice out here, it's 9 feet tall. So again, where do I put that load? This time, just for the fun of it, I think I'll put it right in the middle. Does it make sense? That would be 9 times 8, 72 pounds. So the wall is helping resist it. The roof, to Daniel's point. Yeah, the roof has load too. Notice it's got live load. What would live load be on a roof? I don't put things on roofs and take things off roofs. What's on a roof that's actually alive?
Snow, water,
Yep.
maybe like leaves. I don't know, like wet leaves.
Yep. That's exactly right. Snow is the primary one, just because it weighs so much. Leaves don't weigh that much. Water, because it runs off, won't weigh that much. But you're exactly right. Or people. Occasionally, a person might be up there working on it. But the primary one is snow. Well, that's what that 25 is for. 25 pounds. I'm designing a house right now up by Callahan's, up on the top of the Siskiyous. Does it make sense they get more snow up there than we get down here? So I had to go to this website and I found out what the live load is for the elevation it's at, and it was 70. So I'm having to replace that 25 with 70. So you can't get this wrong. Like, this is something you got to get right. Well, again, notice 15 pounds dead load times 12 feet. Wouldn't it be the same tributary as the, I mean, if the house is 24 feet wide, wouldn't the roof also kind of be 24 feet wide as well? So 12 of it is here. If there's overhang on the roof, that can actually add a foot to that. So it could actually be 13 if you counted the overhang, but we'll keep it simple. So if I take 12 times 15, let's see, 5 times 12 is 60, and I have 3 of those, so that's 180 pounds. Notice that a little more clearly really is acting right on the outside corner because of the way that is attached. So we got the roof resisting, we got the wall resisting, we got the floor resisting. What else? Well, let me ask you. If you walked up to that concrete wall right there, would you be able to push it over even before anything was put on it? Like, isn't it going to be hard to push hard enough on that wall to tip it over if it's made out of concrete? Now, if it was made out of like paper, you could probably do it, but isn't the weight of the concrete itself keeping you from wanting to do this? And concrete is actually a huge contributor because it weighs a ton, literally. So notice it has 2 parts. There's a stem wall, 150 PCF. What's PCF stand for? Pounds per cubic foot. So you got this stem wall. Notice it's 8 feet tall and it's 8 inches wide. And remember, it's a foot thick. So you have an 8 foot by 8 inch by 1 foot chunk of concrete there. You got to figure out how much that weighs. And wouldn't that be right here in the middle? The stem wall, pounds. Wouldn't that be right there in the middle? And then lastly, you also have the footing. Still made out of concrete, still weighs 150 pounds per cubic foot. but notice it's 1 foot thick and it's 16 inches plus 8 inches plus 28 inches wide. Notice you got to work in feet for everything because it's pounds per cubic foot, not per cubic inch. So you got to work in feet, and then again, it's a foot thick. Where's that going to act? Where's that arrow drawn for that force in that footing? Somebody tell us.
So it's in the middle. So then it would be 20 plus 4 inches from T, 32 inches. So
Yeah, in the middle of the concrete. It's not 32 though. It's in the middle of the concrete. Isn't the middle of the concrete about right there?
oh yeah, oh for the
The middle
footing.
of the wall,
Yeah.
the middle of
So
the concrete. So if the whole thing is 28 plus 8, which is 36, plus 16, which is 52, then it'd be 26 inches over. Does that make sense?
yeah.
And again, what are we doing here? We're doing what engineers do, which is treating that footing like a particle, like the whole thing acts at that center of mass. And so this is the footing pounds. So you have 5 things: roof, wall, floor, stem wall, footing. All of those are to the left side of T. Therefore, they're all resisting the push on this. So this is your first project. See if you can figure out the resisting moment. How much total moment is there? I gave you the first one, 120 times 3. See if you can figure out the rest. This is not an individual project. You're more than welcome to check your answers with other people, have an argument if you disagree. You're more than welcome to check with me and say, is this right, before you turn it in? And I'll say no. And then you'll show me your work and I'll say, well, think about this. And then you'll go back and fix it. Like, don't just turn it in wrong. Can you see though what you're learning right now, applying directly to this real paid job? The only difference is, and I did ask my engineer friend about this when I said, how do you know to pick 28 inches for the toe on this? And he said, I don't. I just pick something and I make all the calculations and I see if that works. So it's pretty arbitrary. Now, would you agree that there needs to be a factor of safety in that? What you're really doing is calculating the overturning moment. And by the way, we'll pick this problem up again later in class when I show you how to figure out where that blue force is right there and what it is. We'll pick this up later and we'll calculate the overturning moment and we'll calculate the resisting moment. And it'll be very important that the resisting moment is bigger than the overturning moment, because if it's not, this is going to tip over. So pretty cool stuff. And it's not that hard. Like, this is exactly what you're learning right now. It's just more realistic because there's not arrows pointing at it from nowhere. All the forces are, well, arrived at by you based on commonly agreed on numbers. This is the real roof load for the valley that we live in. There's not a lot of snow here. So 25 pounds, that's the real roof load. This is the real floor load for houses I designed. 40 pounds live, 10 pounds dead. That's the actual weight of concrete. I looked it up online. Like, this is a real problem.
Hey, Doug,
Yeah.
is the soil is gonna have a force acting on a
Yes.
concrete pad? Yeah.
Yes, I forgot that one. Thank you. Let's get that one in there. There's one more and I forgot it. So would you agree that you have kind of a stack of soil right here sitting on top of that? And notice it says right there that it weighs, and again, I looked this up online, it weighs 120 pounds per cubic foot. So notice there's 16 inches wide of it, and it's also 8 feet tall. Where is it going to act? Where is that arrow going to be? I need to reduce all that soil to one arrow. Where is it going to be? Where's it going to be, Evold?
Is that inches, right? I can really see. This is that 6 inches?
Is that better?
Yeah. So it's gonna act, I think, at 3 foot, right?
That's 16.
Oh, is
That
that?
that width from there to there is 16.
Oh, then 8.
Yeah, the key is right in the middle. Does that make sense? So it's going to act right there in the middle, 8 inches in. So however much that soil weighs, and you got to know where that is, because that's, the key is like, how far is that away from T? What's its distance? Does that make sense?
Mm-hmm.
So we'll call that the soil in pounds. So I guess there's actually 6 loads, 6 different loads that you're going to have. So see if you can come up with this. Now, when I say project, I mean due in a week. I mean due in quite a while. It's not due right away. Like when I would do it, if I would, well, I don't know. This is good prep for the test on Tuesday as well. But after the test, you sort of don't have anything to do until I teach you something new on Thursday. So you could do it Tuesday, Wednesday, Thursday, like after the test is done. Tuesday and Wednesday, somewhere in there. So I'm going to post this. I'm going to post both of the notes, and then I'm going to post a blank copy of this that we did today, so that you can kind of start from scratch and sort of make sure you can understand all of that. I want to take a quick second and actually, let's do this in my open math. So you're all seeing this, right? You probably haven't went here yet, but in here is your exam 1 test notes, the class notes that I post every day, and then test review. So exam 1 review solution. So we're taking a test on Tuesday. So that's all you're going to do. I sent you an email about that the other day. Effectively, it's going to open up at 11 and you're going to have a couple hours to work on it. And then you're going to send it back to me. Let's see. I'll probably just post it right here where it's easy to see, like right there. I'll probably post it right here. So it'll just say midterm 1. And it would be ideal if you scanned it and sent it back to me right inside my open math, not emailed to me, but I'll send you a little set of directions about that. But you need to spend some serious time between now and Tuesday on this review, as well as your homework assignment, because this is me telling you what's on the test and me giving you a chance to practice it. So I will be giving you a question like this, where you had a problem like this before. I just kind of changed the things around, but try not to look at your notes. Try to do it with your brain. Try to do these problems with that note sheet only and your logic. So I'm going to give you a problem like this where you're supposed to come up with the force. Find the forces on members A, B, and AC if this force here is 360 newtons down. I just didn't redraw a picture. I will redraw a picture for the test. Determine the magnitude of the resultant force and its direction. This is a easy problem in the sense that you should convert, just like we did a minute ago on the beam problem, you should convert all 3 of those forces into horizontal and vertical. Add up all the verticals, there's your vertical force. Add up all the horizontals, there's your horizontal force. And then in this case, it says, change that, as we just did a minute ago, change that into 1 force and tell me what angle that's at. Again, my solutions are in here too, not just these problems, but also solutions. Another practice problem of the same exact thing, nothing new. Determine the magnitude of the resultant force and its direction. That's a really important concept. We started with that clear back in chapter 2, and we just saw ourselves using it again today. So it's something that needs to go in deep. 3D, can you do this in 3D? Can you do the same exact thing in 3D? Force B, 880, force C, 540, and you're given dimensions on the ground. Notice it's pulling from A down to C and from A down to B. So can you take that 880 and the dimensions that you're told so you know where it's pointing, and do the same thing. Can you convert that into an X, Y, Z force? So then you have force of Bx, force of By, force of Bz, which you're going to get by multiplying it by the unit vector that this 2, 3, and 6 create, or the proportion that those create. And then do it again for force of C, force of Cx, force of Cy, force of C and Z. Add all the X's, add all the Y's, add all the Z's. Now you got a single answer for X, Y, Z. There's no way you can draw right triangles like you could up here. You could just draw your own right triangles in here. That's what we did today. I just did it scalar method. I just did it by drawing my own right triangles and reasoning it out. Down here, I find myself thinking, I got to be a little more savvy, but you're going to see a question just like this. This is what engineers do. We did a question like this. You lucked out here because I gave you that force already broken into X, Y, Z. 720 in the X, 980 in the, let me blow this up. It's probably too small for you to see. 720 in the X, 980 in the Y. So positive X, positive Y, negative Z. So that's one, so I gave you all those X, Y, Z. That's really great. You're going to need that matrix because this is a 3D problem. And notice it's rotation around a point. We had one matrix for around a point. So this is around point A. And one matrix for the next question, which is around, no, this is another practice problem with O. This is another practice problem around a point. You need to be looking for, is it around a point or is it around an axis? Why is this one worse? It's worse because this time I did not give you X, Y, Z separately. You had to figure it out yourself. I told you that it's 280, but notice in this drawing, you can't really tell where that's pointing. Notice it's not pointing parallel to X, but you can't tell where that's pointing. But then I came back and told you, well, in the X direct, it's actually 64 degrees from the X axis and 122 degrees from the Y axis and 40 degrees from the Z axis. That's where that's actually pointing. I don't know about you, but that doesn't even help me. I can't even picture that. But I have a set of formulas that allow me to convert that with something like 280 times the cosine of this angle. Wasn't that it? 280 times the cosine will tell me the X force. And then I'll be back in the same place I was back here. Oh, good. Now I have the X, Y, and Z. And then I can stick it in that matrix and take its determinant. This problem is really close to what we did today. The ability to take a problem that's got rotation and it's got individual forces on it and reduce it all down to, as this says, a resultant force. And I said, specify its distance from point O along the center line of the beam. We did that at the start of class today. Notice again, it has some random 200 Newton meters out there, just rotating it around point O. And another practice problem of the same kind. Like, this is what we've studied so far. That's what you need to be able to do. And the solutions to this are posted. And I would encourage you, don't look at these until you're just dead. Like, you've tested everything. Don't look at it for 2 seconds and then say, well, I can't do it. I'll have to look at his answers. I mean, come up with an answer, even if it's wrong. Even though you're like, I don't think I understand this. This is probably totally wrong. The reason I say that is because then when you look at what I did, the difference between what I did and what you did might stick out to you a lot more. The average grade on this first test has been like 75% in the 4 or 5 years that I've taught this. And that's because this stuff is kind of hard. And now you're, looking at it all at the same time. And so to me, the larger question is, if you have the test only and you have this sheet, are these speaking to you? And if you're using the assignments as you should, then you're making progress with this stuff. But you got to bug me more. Like, I'm not getting bugged by near enough questions. And again, would encourage you to send me a text and say, hey, can we get together and have a little Zoom about something? I don't care. Like, it only takes a couple of minutes a lot of times to answer your single question. And so take me up on that more. This stuff is hard. I thought it was when I learned it. So this is a pretty cool sheet, but it's packed and every single thing on it is important. And I tried to make it really clear by bolding things. Moment around a point in bold. Magnitude of the moment around an axis in bold. And so, two matrices are using the same determinant technique to multiply them out, but you don't even have to memorize it because I have it written right here, at least to kind of double check it. And the only other thing I would say is just make sure your work is ridiculously clear, as you should be doing anyway. As an engineer, you can't afford to get stuff wrong. Check the stuff really carefully. I say that because you need to get better at that just as a human being, so you don't make math mistakes. But in this case, you're just learning this stuff, and I've got to give partial credit. And a big part of this class is partial credit. And if I can't read your writing, I mean, it's really not acceptable as an engineer that I couldn't read your writing. But just make sure that I can give partial credit when it's due and decipher, what went wrong where. Was it just a calculator button push or whatever? So. All right. Anything else for the good of the cause?
I think about the task is all pretty clear.